In this video, we're going to look at the graphs of tangent and cotangent. Some basic information that we need to know about. This is going to be true for tangent and cotangent, but we'll go through it one at a time. For tangent, the period of tangent is pi, which means we see those values repeat themselves over pi units, not pi over 2, or I'm sorry, 2 pi units like we had with sine and cosine. We have seen in tables that tangent is undefined at certain values. And it's what you would see if you were to continue patterns is that tangent's going to be undefined at odd multiples of pi over 2. So 1 times pi over 2, 3 times pi over 2, but not at 2 times pi over 2, which is pi. Tangent's not undefined at pi. Tangent at pi is going to be 0. Because this function is undefined at these odd multiples of pi over 2, what this is going to result in terms of the graph are asymptotes. All right, so we're going to start with our landmark points for tangent. We're going to keep with 5, but 2 of them are going to end up resulting in our asymptotes. So we're going to start at that negative pi over 2, go to negative pi over 4, 0, positive pi over 4, and positive pi over 2. Tangent's going to be undefined at both negative pi over 2 and positive pi over 2. And tangent of 0 is 0. We just went through that. Tangent of negative pi over 4, if we think about negative pi over 4 and we think about that unit circle, I'm going to quickly sketch that here. So negative pi over 4 is going to be right here. Tangent's going to be negative. The x and the y values there are the same, so tangent is equal to -1 here. And at positive pi over 4, which is right here, again, sine and cosine at pi over 4 are the same value. They're both positive. So tangent of x, which is sine of x over cosine of x, is going to be +1. We're going through this really quickly. I do realize that, but we are using a lot of the stuff that we've already learned. So definitely take some time, pause when you need to, reflect on the things that we're talking about, and try to make sure that the concepts that you've learned in the previous videos are retained in your memory, that you're being able to apply them now. So we're undefined at negative pi over 2, negative pi over 2, and positive pi over 2, which give us those vertical asymptotes. At negative pi over 4 and positive pi over 4. So we're still dividing our period up into 4 equal sections, just like we did for sine and cosine. Negative pi over 4 is tangent's -1. Tangent of 0 is 0, and tangent at positive pi over 4 is 1. And what this is going to look like, and we could plot more points to see this, but we don't necessarily need to, is it makes this nice little S curve. It looks a lot like a cubic function that you might remember from a college algebra class. And this would continue on and on. So a quick sketch of the whole function with multiple asymptotes. We just see that same S curve repeating itself, where what we've graphed is just this one. Looking at the graph of cotangent, so y equals cotangent x, the period for cotangent is also pi. And cotangent is undefined at multiples of pi. And again, when it's undefined, we're going to see vertical asymptotes in our graph. Now, because our asymptotes are going to be different from tangent to cotangent, those landmark points that we're going to use are going to be a little bit different. Remember, we want our landmark points, the two outer points, to be those asymptotes. So that's going to occur at 0 and at pi. Halfway between those is going to be our pi over 2. Here's pi over 4. And here's 3 pi over 4. Cotangent is undefined at 0 and pi. Cotangent at pi over 2, and we can still use the same picture here at pi over 4. We have sine and cosine are the same. Remember, cotangent is the reciprocal of tangent, so it's cosine of x divided by sine of x. So it's still going to result, I'm sorry, pi over 4, not a pi over 2. Result at 1. Cotangent at pi over 2. So again, thinking about this, where we've got the ordered pair 0, 1. Cosine divided by sine is going to be 0. At 3 pi over 4, we're over here where our x is negative, our y is positive. So it's just going to change the sign of cotangent to be -1. So marking our asymptotes, we've got the y-axis as an asymptote and pi. We're going to divide this in half twice. Cotangent of pi over 4 is 1. Cotangent at pi over 2 is 0. Cotangent of 3 pi over 4 is -1. So we have a similar shaped curve, but looks like it's reflected about the x-axis. And just like with tangent, we're going to see these different branches repeated. We're just looking at one period here. All right, so I've summarized the transformations similar to the way I summarized the transformations for sine and cosine. Because tangent and cotangent have the same period, we can switch out the forms here for cotangent without any other changes. Again, we've got form 1 and form 2, which are really going to mainly impact what that value of C represents. So A, we don't really have amplitude in tangent and cotangent because we don't have maximum and minimums. If we look at these graphs, they go on forever and ever in both directions. So the range is -infinity to +infinity. We have no extrema there. But we do use A to identify our landmark points. Primarily those points here and here, here and here. That's going to be determined by that value of A. B is still our frequency. It determines the number of periods over pi now, because again, the period for tangent and cotangent is pi. So we want to be really mindful of those differences between sine and cosine and tangent. So the period of any one of these functions is going to be just pi divided by b. Depending on the form, your phase shift is going to either be C over B if we're in this first form, or just C if you're in that second form. And we're going to use the same idea of the phase shift helping to determine where the vertical asymptotes for the function are located. We're going to set your argument equal to pi over 2 if it's tangent to find that first asymptote, or 0 for cotangent to find that first asymptote. And then D is our midline, again, just that vertical shift up or down. And that's really going to help us identify this midpoint here. All right, so graphing y equals tangent of 2x. That 2 is going to represent our value of b, so we want to use that to find our period. And to find the period, it's going to be pi divided by b, in this case 2. We don't need to simplify this. To find our asymptotes, we're going to take our argument and we're going to set it equal to pi over 2 in this case. So our argument is 2x. We're going to set this equal to pi over 2. And again, the reason we are setting it equal to pi over 2 is because we're dealing with tangent. When we see an example of cotangent, we're going to shift that and set it equal to either 0 or pi to find an asymptote. Dividing both sides by 2, we've got our first asymptote at x equals pi over 4. We're going to use that first asymptote, the same idea as our starting point in our graphs for sine and cosine. So I'm going to mark pi over 4 here. This is our first asymptote. And from our first asymptote, we're going to graph our next asymptote using the period. The period is pi over 2, which is 2 pi over 4. So I'm going to go another pi over 4 and another pi over 4. So this is 1, 2, 3 pi over 4 is our next asymptote. Or we could go to the left. Here's 1 pi over 4 and then another 2 pi over 4. There. So we've really set up asymptotes in both directions so we could graph 2 periods of this function. Remember that tangent looks a lot like that cubic function. So starting at that minimum, going to the midline, going to the maximum. Since our amplitude or that value of a did not change, we're still dealing with those values of -1 and 1. We're going to divide our periods up into 4 equal sections, starting at, and I'm going to say minimum. It really isn't the minimum, but it's just a force of habit from what we were working with sine and cosine. But starting at that -1, going to the midline, going to +1. Same with the next period at that first tick mark past pi over 4, we're at that value of -1, then we're at our midline, then we're at +1. So this is illustrating 2 periods of y equals tangent 2x. Y equals -3 tangent of 1/4 x. So our amplitude, again, it's in quotes. We don't really call it an amplitude, but it is going to be helpful in those landmark points. Amplitude is 3, and we're going to reflect about the x-axis because of that negative out front. So just a quick sketch of what that's going to look like. If I've got my 2 asymptotes, instead of going from bottom to top, we're going to start at the top and go to the bottom. So we're going to see that decreasing branch. The period is going to be pi divided by 1/4. Again, it's pi now in the numerator because the period for tangent is pi, which is 4 pi. To find our asymptote or our starting point, we're going to take our argument 1/4 x, and we're going to set it equal to pi over 2, that first positive asymptote from our parent function. Multiplying both sides by 4, x is going to be equal to, let me write this out to see it better, 2 pi. That's going to be our first asymptote. So we'll call that 2 pi. Since our period was 4 pi, I'm going to go now to the left just to show that one center branch. So starting from 2 pi and going 4 to the left. 1, 2, here's -2 pi. And our second asymptote. Our amplitude was 3, which is just going to change how we mark that vertical axis. It's not really going to change any physical height. That's one of the nice things about graphing. And that reflection means we're going to start at the top and go to the bottom. So at this landmark point, in this case, it's going to be pi. We're at +3, then we're at our midline, then we're at -3. And there's one period of y equals -3 tangent of 1/4 x. Y equals 3 cotangent of 2x minus 3 pi over 4. Our amplitude is 3. Our period is going to be pi divided by 2, and that's not going to simplify. And then we're going to find our asymptote, our first asymptote, in order to help us graph that, identifying that phase shift this way. Let me set it equal to 0 because that's what we have in our notes. Again, the choice of 0 is because we're dealing with cotangent. And if we look at our parent functions for cotangent, we have asymptotes at 0 or pi. So you could really set that argument equal to 0. You could set that argument equal to pi. It makes no difference. You're just trying to use one of these these parent function asymptotes to help identify the new asymptote for this function. Subtracting 3 pi over 4, we get 2x is equal to +3 pi over 4. And then I'm going to multiply by 1/2. And I'm just illustrating that, even me, sometimes I have a hard time processing some of this arithmetic in my head. So writing it out is really helpful. 3 pi over 4 times 1/2 is going to be 3 pi over 8. So we're going to start with our first asymptote at 3 pi over 8. We do not have any change to our midline. Since our first asymptote's at 3 pi over 8, a good idea is to start making increments of pi over 8. So here's 1, 2, 3 pi over 8. Then 4, 5, 6, 7, 8 pi over 8. So there's pi. When we think about our period of pi over 2, we probably want to think about it in terms of pi over 8. It's like how many of those units do we need to go to find our next asymptote? So we might just multiply this by 4 over 4 or 4 pi over 8. So I know I need to go 4 units to the left or to the right to get another asymptote. So from 3 pi over 8, 1, 2, 3, 4. 7 pi over 8 is going to be our next vertical asymptote. Now the amplitude was 3, so we've got 3 and -3 marked. In between these two asymptotes, cotangent starts at the top and goes to the bottom from left to right. So at that first mark inside my period, I'm going to be at +3. Then I'm going to be at my midline. The last mark of my period, inside of my period, is going to be down at -3. And there's our sketch of that graph. Now, if we wanted to continue, graph another period, let's go to the left to graph another period. So I've got starting at 3 pi over 8, going 4 pi over 8s to the left. I'm going to have to go down here to -pi over 8 for my next asymptote over here. And it's the same thing. We're going to start at that first tick mark, which is actually going to be that y-axis at +3, then our midline, then -3. And there's another branch of our graph. Y equals 2 tangent of 2x minus pi. Our amplitude is 2. Our period's going to be pi over 2. To find our asymptote, we're going to take our argument 2x minus pi. We're going to set it equal to pi over 2, that first positive asymptote from our tangent parent function. Adding pi to both sides, we get 2x is equal to 3 pi over 2. And then dividing both sides by 2, x is equal to 3 pi over 4. So that's going to be our first asymptote. Another thing to observe, our midline did not change at 0. So that's why I do have my horizontal axis centered in the middle. Because our first asymptote occurs at 3 pi over 4, we're going to go by units of pi over 4. So I'm spreading this out a little bit more than others. And then our period is pi over 2. So again, you might want to convert that to something over 4. So 2 over 2 or 2 pi over 4. So if 3 pi over 4 is our first asymptote, I can go left or right to find 2 units or 2 segments in order to get another asymptote. So pi over 4 is going to be another asymptote. So is 4 pi, 5 pi over 4. Tangent starts at the bottom and works its way to the top. So we need to do some more division of our period into 4 equal segments. Our amplitude is 2, so we're going to mark the vertical axis. So we're here at -2, midline, +2. We can draw one more branch, -2, midline, +2. Determine an equation for each of the graphs. All right. So this is a great visual of what the graph would look like generated by Desmos for a tangent or a cotangent graph. We have some options here as to identifying whether or not we want to use tangent or cotangent. Similar to our previous videos with sine and cosine, any graph like this can be represented by a tangent function or a cotangent function. So typically we try to observe which one is it most closely related to without having to do a phase shift, and that's where we go. But sometimes we can't avoid a phase shift, plain and simple. Because we intersect that value of 0, 0, we're actually going to start with our tangent function. It also, we see that increasing branch. So this does look like a tangent function with no phase shift. All right, so we've got our equation y equals a times tangent of bx plus d. Again, I don't have a plus c because we don't need a phase shift here. We can also see that the middle of this graph, the midline is 0, so d is going to be 0. So we can get rid of that d altogether. Now, on this graph, I'm going to start sketching my asymptotes because I think it's a little, they're not going to display the way we draw them by hand. So I think drawing them or adding them to the graph is helpful. So we've got an asymptote at whatever this x value is and whatever this x value is. If this is 2 pi, this is pi, which means this is pi over 2 and negative pi over 2. Because we see one branch from negative pi over 2 to pi over 2, that means our period is pi, which is the same, which tells me that b is equal to 1. Let me clarify. because the period of pi is the same as the period of our parent function for tangent. There's no change in the value of b. Now, thinking about this section, and I'm going to try to zoom in a little bit further. Oh, this is about as far as I can go. I'm going to do some cleaning up here. Keeping my asymptotes. But what we're going to try to do is divide that segment between the two asymptotes into fours. So there's midway, here's midway, there's midway. And really what we're looking at is where does this quarter segment intersect and what's the height? So it looks like that's at 1, 2, -3 and +3. So that tells me that my amplitude is 3. So my equation is y equals 3 times tangent of x. All right, looking at this example, my first observation is that my graph does not intersect that 0, 0. We actually have an asymptote here at x equals 0. So I'm going to use cotangent. Now, if we look, we're not intersecting the middle of each branch at that x-axis, which means that we have a midline shift. It looks like the middle of these branches are about there. That middle is where the graph changes from concave down to concave up. Also called an inflection point for those of you who move on to calculus. Which means, actually, let me keep one of those. Our midline is at 1. So we know d equals 1. Our period for this equation, so thinking about where our asymptotes lie, we've got an asymptote at 0 and another one at 2 pi, which means that our period is 2 pi, which is equal to pi divided by b. We're going to solve this equation for b by multiplying both sides by b. So we have 2 pi times b is equal to pi. We divide both sides by pi. Sorry, we want to divide by 2 pi. B is equal to 1/2. Now the amplitude, I'm going to also sketch on my graph the midline of +1. So our period from 0 to 2 pi, there's the middle half and then another half. And at those quarter points, this is where we want to see the height. So we have that at 2 and this at 0. The distance between the midline and the points where those landmark points is going to be 1. So our amplitude is still 1. One other observation to make is that cotangent typically starts from the top and goes to the bottom. Since we're starting from the bottom and going to the top, then we have a reflection about the x-axis. And that reflection is illustrated in the equation by making the amplitude negative. So our equation, we're using cotangent. It's -1 times cotangent of 1/2 x. We do not have a phase shift, so we can close the parentheses and our midline is 1.